Hi, my name is Aiden, and this is Lab 4. So the purpose of this experiment is to demonstrate the motion of a mass on a spring as it oscillates from a fixed point. And with this, we'll validate that the potential and kinetic energy are conserved as stated in the energy principle. So by tracking an experimental video using software and comparing it to a predicted motion program, we can demonstrate the accuracy of Newton's second law, and of course, in the energy principle. And here's a small preview of the results. We can say that the total energy in the system remained at zero, which validated the energy principle, and that the experimental motion followed very closely with the computational model. So the momentum principle describes how the net force acting on the system creates a change in momentum over time. Therefore, we have these formulas. With this principle, we can derive the velocity update and position update formulas. So the energy principle states that energy cannot be created or destroyed, and that the change in energy of a system is equal to the work done by the surroundings. With this, we can define the system in the problem to be more convenient for us. If the system includes the mass, spring, and earth, it can be said that there are no forces in the surroundings doing work on the system. Therefore, we can define the following kinetic and potential energies as making up the total energy. So here in this problem, we have spring potential energy, gravitational potential energy, and kinetic energy, and these add up to the total energy. So before tracking this motion, the spring, and mass, we calibrated the tracker software and tracked each frame for the data. So here we just have a video of the tracker software running. As we can see in both the Y and X directions, we have this oscillatory motion, which is what we're looking for. And here we have the data that we will use in the next portion. So using the data from the tracker program, we could find some initial conditions. So the system we're defining as the mass, spring, and earth, and surrounding is everything else. So the mass of the mass and spring were 0.406 grams. These were the initial X and Y positions. This is the initial time. This is the spring constant of the spring, and this is the relaxed length of the spring. And since the mass starts at rest, we can say that the initial is 0. So here are just the initial conditions for the glow strip model. We have the mass, its initial position, velocity, and its initial spring conditions. So here we have the update formulas for the glow strip model. Here we have the force of gravity, which is defined as negative mass times gravity. Here we have the force of the spring, which is just defined as the negative spring constant times the difference between the current length and the relaxed length times the unit vector in the direction of the spring force. And then we have the net force by just adding the force of gravity and the force of the spring. And here we just have the Newton's second law position and velocity update formulas. So here's some more update formulas. We have updating the spring, and here we have the kinetic and potential energies as mentioned before. We find the change in energy by subtracting the initial from the current energy. So these are the experimental versus predicted graphs of position. As you can see, they follow fairly closely, although there are some discrepancies, and we can attribute these to errors in the forces, which we'll explain later. So here is the energy graph for the predicted model, and the potential energies of the system are constantly changing between each other, but the total energy remains constant at 0. So what are some sources of error? Primarily, we cannot count for all possible forces, namely air friction would do work on the system, which would change its total energy and velocity. And overall, there would be energy dissipating from the system into the air and atmosphere. But the energy principle is still satisfied. Based on the graphs, the total energy of the system remained at 0, which transformed between potential and kinetic energies. And even if energy dissipated in the experimental or real-life video, it was conserved because it was transferred, not destroyed. And what if we estimated the period of oscillation? Well, first we could define these 3 periods for both the x direction and the y direction. The average x period was this time divided by 3 for each of the periods, which ended up being 1.804 seconds. And the average y period was getting each of these, the time after each of these periods, and dividing it by 3, which ended up at this time. So the period of oscillation for the y direction is slightly faster than the x direction, and we can actually attribute this to drag or air resistance being unaccounted for. So if we accounted for those forces like before, it would make a more realistic energy approximation and more realistic position and period. Thank you.